we'll talk about other types of aromatic compounds, including anilines, polycyclic aromatic hydrocarbons, aromatic ions, heterocyclic aromatic compounds, and also the effect of aromatics on acidity, basicity, and SN1/E1 reactions. I've posted these slides on Canvas for you to print out or take a look at later. Some of the molecules that I've shown are very complicated. I do not expect you to draw them, but you can go ahead and print out the slides and follow along with the video and take additional notes. Before we get started, let's just review the criteria for aromaticity. Now, in order for a molecule to be aromatic, all of the atoms involved in the conjugation must be sp2 hybridized. The molecule must be a planar ring, and it needs to contain Huckel's rule number of pi electrons. So remember that we need an odd number of electron pairs, or we can follow that 4n+2 formula. But either way, we are going to be looking at molecules that contain 2, 6, 10, 14, 18, or 22 pi electrons, and it needs to have those numbers in order to be considered as an aromatic molecule. Anilines are defined as conjugated monocyclic hydrocarbons. So benzene, by that definition, is an aniline. Now the name that we use for benzene as an aniline is 6-aniline. Now the 6 in brackets can either stand for the number of carbons or the number of pi electrons. For anilines, those numbers are always going to be the same. Now we learned in the previous video that benzene is aromatic. It follows all of the criteria for aromaticity. All of the carbon atoms are sp2 hybridized. It is a planar ring, and we also are in agreement with Huckel's rule for the number of pi electrons, in that we have 3 pairs for a total of 6 pi electrons. Now, cyclooctatetraene is another name for 8-aniline. So this name here, cyclo meaning it's a cyclic structure, octa meaning it contains 8 carbons, tetraene means that we have 4 enes or 4 pi bonds, which we can see here. Now, for 8-aniline, it is a non-aromatic compound. And that's because even though it does contain all sp2 hybridized carbons, the 8-aniline actually adopts more of a boat shape that we see here. So it is in fact not planar. And if it's not planar, it means that it cannot follow any of the criteria for aromaticity, which will make it non-aromatic. In addition to that, we have 8 pi electrons, which does not follow Huckel's rule. So there's a couple of things wrong with the 8-aniline that is going to make it non-aromatic. So to focus on the anilines that we would expect to be aromatic, let's go ahead and focus on Huckel's rule. Now, based on Huckel's rule, we would expect anilines with 2, 6, 10, 14, etc. pi electrons to be aromatic. Now, there is no such thing as a 2-aniline. We cannot take 2 carbons and have them turn into a ring. We already know that benzene with 6 carbons and 6 pi electrons is aromatic. So now for 10 anilines. So 10 anilines are actually not planar. There's too much ring strain associated with a 10-aniline that is going to turn it into more of a bent structure. So as a result, a 10-aniline is very similar to an 8-aniline. Because it is not planar, it's going to make it non-aromatic. Now 14 and 18 anilines, because there's a large number of carbons, they're able to space themselves out so that the molecules become planar, or planar enough to be considered aromatic. So a 14 aniline is actually not entirely planar, but it is planar enough to have the proper overlap of the p orbitals of all of the carbon atoms. 18 anilines, which is this structure here, is completely planar and is therefore aromatic. We can also have aromatic compounds that are polycyclic, meaning multiple rings are fused together. So these are just some examples of some aromatic polycyclic hydrocarbons. And you'll notice that if you take a look at all of the atoms in these conjugated systems, all of the atoms are sp2 hybridized. Now these polycyclics are also all completely planar, and you'll notice that they all follow Huckel's rule in terms of the number of pi electrons. This one, naphthalene, has 10 pi electrons. Azulene also has 10 pi electrons. And the phenanthrene, has 14 pi electrons. Now it's important to note that with polycyclic aromatic hydrocarbons, they don't necessarily need to follow Huckel's rule, but the majority of them will, as you see with these examples here. Ions are also capable of being aromatic. Now in our first molecule, we're going to pay close attention to the carbon containing the lone pair here. Now as you can see, the other 4 carbons are all sp2 hybridized, and we currently have a total of 4 pi electrons. Now this carbon containing the negative charge, normally a carbanion is sp3 hybridized. However, if this carbon were to be sp2 hybridized, the lone pair could be in the unhybridized p orbital. At that point, this sp2 hybridized carbon would complete the ring. All 5 carbons would be sp2 hybridized. We would have our overlapping p orbitals, and this lone pair, which would be located in a p orbital, would now be considered pi electrons. So we would have a total of 2, 4, 6 pi electrons, which follows Huckel's rule. So really, this carbon is sp2 hybridized. And the lone pair are located in the p orbital. Because they're in the p orbital, they are considered a delocalized lone pair. Now we saw this concept back with resonance structures as well. So let's go ahead and redraw the structure. So really what's happening is these lone pairs are not localized on this carbon. They have been donated into the ring, allowing all of the other pi electrons to move around. Okay, so at this point, we have 6 pi electrons. And we now have an aromatic compound. So another way of drawing this molecule is by drawing a 5-membered ring. Draw a circle to indicate the fact that all of those pi electrons are moving around. And then it is a negatively charged molecule, so we want to indicate that with a negative charge in the middle of the circle. So this is called an aromatic anion. And it's an example of an ion that is aromatic. We can also have aromatic cations, as shown in the second example. So again, we have a whole bunch of carbons here that are sp2 hybridized, and we have a carbocation here. Now we learned in OChem 1 that carbocations are also sp2 hybridized. Now in this case, this carbon does not have a lone pair, so it actually has an empty p orbital. But it provides a p orbital to allow these 6 pi electrons to move constantly and continuously around the ring. So at this point, we have all sp2 hybridized atoms, we have 6 pi electrons, and we have a planar ring. So this is an aromatic cation. All of these electrons can move around amongst all 7 atoms. Now we can redraw this similar to the structure above. We have our 7-membered ring with a circle to indicate the fact that all of the pi electrons are moving around. And since this is a positively charged molecule, we're going to draw that positive charge right in the middle of that circle. So this is an example of an aromatic cation. So let's go ahead and do a few practice problems with 3 anions. And we want to determine if they are aromatic, non-aromatic, or anti-aromatic. So just to recap, our criteria for aromaticity is sp2 hybridization, planar ring, and Huckel's rule number of pi electrons, 2, 6, 10, etc. So let's go through each one of these molecules. So we're going to be focusing on the ring only. This methyl group is not involved in the conjugated system, so we don't need to worry about the hybridization of this methyl group. So for this carbon, it's a carbocation. We know it's sp2 hybridized, and these two are sp2 hybridized as well. So for our first molecule, we satisfy the criteria for sp2 hybridization. Now a 3-membered ring is planar. There's no way for it to bend to become not planar. And as for the number of pi electrons, we have 2 electrons here. So 2 falls under Huckel's rule. So we do satisfy Huckel's rule for the number of pi electrons. So we satisfy all of our criteria. That's going to make this first compound aromatic. For our second compound, we have 4 carbon atoms that are sp2 hybridized, as well as a carbocation that is sp2 hybridized. So all of our atoms are sp2 hybridized for our second molecule. This is a planar ring, and for most of these problems, you can assume that the rings are planar unless otherwise stated. But for this one, this 5-membered ring is always going to be planar. Now for our number of electrons. We have a total of 2, 4 pi electrons. There's no negative charge or lone pair here that can make it up to 6. So we do not follow Huckel's rule in this case. Now, anytime we satisfy the first 2 pieces of criteria, but not Huckel's rule, it's going to make the molecule anti-aromatic. So now let's go on to the last molecule, number 3. Now with this one, we have 1, 2, 3, 4, 5, 6 carbons that are sp2 hybridized. Now the 7th carbon contains an anion. Now normally an anion is sp3 hybridized in the case of carbon. Now if this were sp3 hybridized, it would make this molecule non-aromatic. We wouldn't even satisfy the first piece of criteria for aromaticity. However, if this carbon were to become sp2 hybridized and donate its electrons to the ring, we would satisfy our first piece of criteria for aromaticity because now this carbon would be sp2 hybridized. Now in that case, we would donate the electrons, we would satisfy our rule, we would know that we have a planar ring, but when we come to count the number of electrons involved in aromaticity, it's actually going to be 8. So we're starting off with 6 pi electrons here. 6 actually satisfies Huckel's rule. However, if this were to become sp2 hybridized and donate its electron pair, we would now have 8 electrons in the ring. So this carbon has a choice. It can either remain sp3 hybridized, which would make this compound non-aromatic, or it could be sp2 hybridized, which would give the compound the wrong number of pi electrons and make it anti-aromatic. When a molecule has a choice like that, it's going to stay non-aromatic. So anti-aromatic is a very unstable form for a molecule. If a molecule has a choice, it would prefer to be non-aromatic. So in fact, this carbon is going to remain sp3 hybridized, which will make this compound non-aromatic. Aromatic compounds are also not limited to carbon. They can contain other elements, the most common ones being oxygen, nitrogen, or sulfur. So all four of these molecules are examples of heterocyclic aromatic compounds. Now remember, our criteria for aromaticity is we have to have sp2 hybridization. We need to have a planar ring. And we need to have Huckel's rule number of pi electrons. So 2, 6, 10, etc. So let's take a look at each one of these examples. So in our first example, we have a ring. It is a planar ring. We have 1, 2, 3, 4, 5 carbons. All 5 of these carbons are sp2 hybridized. Now this nitrogen is also sp2 hybridized. It is bound to 3 things. Now the lone pair for this nitrogen are located in an hybridized orbital, sp2 hybridized. So these are localized lone pairs. They do not participate in aromaticity. For the nitrogen's p orbitals, these pi electrons here are the ones that occupy the p orbital. So we have a total of 6 pi electrons, all in the form of double bonds within the ring. For our other 3 compounds, we can see 4 pi electrons each. That means the 6 electrons are going to come from a pair of the lone pairs of the nitrogen, oxygen, and sulfur. So for nitrogen, it's going to donate its lone pair into the ring, similar to what we saw with the aromatic anion. For oxygen, it's going to donate one of its electron pairs, and for sulfur, also is going to donate one of its electron pairs. So the atoms donate an electron pair to complete their pi system. So by doing this, all 3 atoms become sp2 hybridized, and we also have Huckel's rule number of pi electrons. So that is going to make them aromatic. As we're going to see in later chapters, nitrogen-based compounds are often used as weak bases in organic chemistry. That's because nitrogen contains a lone pair, and since nitrogen is less electronegative than oxygen, it's more willing to donate that lone pair, thus making it a good weak base. So let's go ahead and see how aromaticity can affect the basicity of a nitrogen atom. And we're going to compare these 2 aromatic compounds. We have pyridine and pyrrole. Now in pyridine, we have the aromaticity that comes from all atoms being sp2 hybridized, and we have the 6 pi electrons. So these lone pair here are not participating in aromaticity. However, in pyrrole, it's necessary for this lone pair to be donated to the ring in order to convert this nitrogen atom to sp2 hybridization and get the correct number of pi electrons. So currently we can see 4 pi electrons here, but we need 6 in order to meet Huckel's rule and have aromaticity. So when comparing these 2 molecules, this lone pair is localized, meaning it doesn't participate in aromaticity. So that is going to make these lone pair more likely to be donated and the nitrogen in pyridine more basic. So pyridine itself is considered weakly basic. However, with pyrrole, these lone pairs are necessary for aromaticity. That means the nitrogen has donated its lone pair to the ring, and our total of 6 pi electrons are now circling around the ring in aromaticity. So these lone pair are currently occupied. They have no potential of being donated because if we were to take them away from the ring, we would destroy the aromaticity of the compound. So pyrrole itself is not basic at all. And that's because the lone pair are occupied. So whenever we're considering the basicity of an atom, we want to consider what the lone pair are doing. If they are participating in resonance or in aromaticity, they're not going to be basic at all. However, if they're localized and just kind of hanging out there on the atom, they're more likely to be donated. Now let's also see how aromaticity can affect acidity. So we know that hydrogens attached to carbons are not very acidic. Now when they are attached to sp3 hybridized carbons, they have a pKa of about 50, which is the least acidic type of hydrogens we have. Now if they're attached to sp2 hybridized carbon, it has a pKa of about 45, so a little bit more acidic. Now when it's attached to an alkyne, an sp hybridized carbon, has a pKa of around 25, which is really one of the more acidic types of hydrogens attached to a carbon. Now let's go ahead and take a look at this molecule. We have two hydrogens attached to an sp3 hybridized carbon. These hydrogens actually have a pKa of about 16, so it's even more acidic than hydrogens bound to sp hybridized orbitals. So let's see why that's the case. Now, this molecule as a whole is considered non-aromatic, and that's because it contains an sp3 hybridized carbon. However, if we take this molecule and treat it with a base, the base will take one of the H's and give the electrons to that carbon atom. Now we create an anion with a negative charge on that top carbon. Now, if this carbon donates these electrons to the ring, it would now become sp2 hybridized, thus making all of the atoms sp2 hybridized, and we would have a total of 2, 4, 6 pi electrons. So by treating this molecule with a base, we've now converted it to an aromatic anion. So converting a non-aromatic compound to an aromatic compound is very favorable. Which explains why this compound is so acidic. It's most willing to be reacting with a base. So you can kind of think of aromaticity as similar to the R in area. R is usually for resonance. If the resulting electrons are stabilized by resonance, it's going to make that molecule more acidic. So the R in this case is similar to the aromaticity. The resulting lone pairs that we get here are stabilized by aromaticity, and that's going to make this a very favorable acid-base reaction. So similar to our R in area, the conjugate base is stabilized by aromaticity and makes the molecule more acidic. Lastly, we'll talk about aromaticity and leaving group ability, specifically in SN1 and E1 reactions. So if we are considering these two substrates here, and we're trying to determine which is the best substrate for an SN1 or E1 reaction, we have to think about the mechanism for SN1 and E1 reactions. Now the rate determining step for these reactions is the formation of a carbocation. So in terms of these substrates, we want to think about which one is going to give the most stable carbocation. Now we have a tertiary substrate here and a secondary substrate here. Now once our leaving groups leave, we will form a tertiary carbocation and a secondary carbocation. So we know that the tertiary carbocations are the most stable, so that's going to make our tertiary substrate the best substrate for an SN1 reaction. Now let's go ahead and consider these three compounds. So taking a look at these compounds, we have a secondary substrate another secondary substrate attached to a ring, and another secondary substrate also attached to a smaller ring. So on the next slide, let's consider the carbocations that are going to form from each of these secondary substrates. So for our first compound, the bromine can leave and form just a regular secondary carbocation. For our second one, we're going to have the bromine leave. We will form a 7-membered ring with a positive charge. Now, let's consider this carbocation. Now, after the bromine leaves, the top carbon is going to be sp2 hybridized. All of the other carbons are sp2 hybridized. We also have 2, 4, 6 pi electrons. So what we've done here is we have formed an aromatic cation. Now let's consider our last substrate. Once our bromine leaves, we will form a 5-membered ring with a positive charge. Now with this carbocation, all of our atoms are sp2 hybridized, and we have a total of 4 pi electrons. This is actually an anti-aromatic cation because it has all of the criteria, sp2 hybridization and the planar ring. However, it does not follow Huckel's rule in terms of the number of pi electrons. So as far as our best substrate for SN1 or E1 reaction is going to be the one that forms the aromatic cation. Our worst one is going to be the one that forms the anti-aromatic cation. And the reason that this is the worst is because you're essentially taking a non-aromatic compound and converting it to an anti-aromatic compound. Now, anti-aromatic has much higher potential energy and is much more unstable than just a regular non-aromatic compound. So we're essentially taking this molecule and making it worse. Whereas with the aromatic cation, the best substrate, we're taking a molecule and we're turning it into something that's much more stable. So these are the things that we want to consider when we are judging the different types of substrates for SN1 or E1 reactions, or any other reaction involving a carbocation intermediate.